Terrain is
something that is there across a long thing.
When it has like certain characteristics.
Some special characteristic that are
okay,
present.
were you up one or?
Something that's present across a regional scale.
Regional. When it has like certain characteristics.
Basic.
Good, okay. Different stratigraphy as well, okay? A terrain is a segment of... Sorry, I didn't do it that way. So, a terrain is a segment of the Earth's crust which has a distinctive sedimentary, tectonic or whatever history from neighbouring terrains, and at some point becomes juxtaposed with them, and from that time of juxtaposition then shares a common history. So these are the terrains that are identifiable within Scotland. We've been progressing through them during this course so far, and we're now in the Southern Uplands. Well, we're not literally, but we've almost been there. So, as we know, the Southern Uplands lie to the south of the Midland Valley, separated from the Midland Valley by the Southern Upland Fault, which is this fault going down there. They lie to the north of the Iapetus Sucia, which is shown by this line going across the map. And you will have noted that that line going across the map does not appear on the large-scale map of Scotland that you looked at the start of the practical, and that's because that line is rather sadly buried by younger rocks, primarily Carboniferous and Devonian rocks. And the Southern Uplands consist of Ordovician and Silurian sediments, as you should know by now, that were deposited in a deep marine environment, and we can divide the Southern Uplands into three major parts. Ordovician in the north, a region that we call the Northern Belt. So that's this bit here, where the rocks are Ordovician in age, Granite and Ashgill. It is separated by a fault, shown in red there, called the Orlock Bridge Fault, from Silurian rocks to the south. And these can be divided into a central belt, where the rocks are Llandovri, early Silurian in age, and a southern belt where the lower Paleozoic rocks are Wenlock in age, mid-Silurian. So you should have got that from the first question in the practical. And you should have realised that it gets younger to the south. The Southern Uplands is in a critical position because it is very close to the line of closure of the Iapetus Ocean, so it provides some of the best information that we have about how the ocean actually closed, or potentially can provide that information. And there are two different views on this. The first is illustrated by these paleogeographic maps, and is based on faunal reconstructions. Hang about, I hear you say. What's a faunal reconstruction? Is that when I stick a pygidium of a trilobite to its thorax? Or a theca onto a graptolite? Is that reconstructing fauna? Or if you're more advanced, sticking a toe bone onto a ichthyosaur? What is a faunal reconstruction in this context?
Reconstructing what fauna was present in that region.
Reconstructing what fauna is present in that region. So that might tell us the environment.
Yes.
And and
Or
the
both
age.
age and environment.
Rocks.
Anything else that we might mean by faunal reconstruction? No idea?
Dinosaur.
Well, I happen to know that Margaret's talked about this to you within the last few weeks. No, not the environment they lived in specifically. It's utilising the fact that where there are large oceanic separations, shelf fauna on one side of the ocean cannot migrate to the other side of the ocean if the ocean is wide enough. Okay, you should have learnt this from Margaret. If you want me to put it in non-expert paleontological terms, I can do my best. Imagine that you, this is called the empathy part of my course today. Imagine that you are a trilobite larva. That's spelled L-A-R-V-A rather than something that's more interesting. There we go. Imagine you're a trilobite larva and you are in Laurentia in the Arenig. Okay? And trilobite larva, what's their mode of life? They're planktonic, okay? So, you as a trilobite larva fancy a little swim, and you drift off a little bit to the south from Laurentia, and what happens to you?
You get eaten. You die.
What happens to you first? You get mature. You develop into a big grown-up trilobite, as opposed to a little larval trilobite, and you found yourself in the middle of a large ocean with nothing to go and feed on, and basically you snuff it.
You what?
Okay? So, you fall to the bottom and you do not get across. So, the point is that larval stages of benthic organisms cannot cross wide oceans. They can cross narrow oceans of a width that depends on how long they exist in a larval stage. So this means that we develop provinces, what are called faunal provinces, that are characterized by different groups of benthic organisms on different sides of a major ocean. Okay? And this is why, for example, we don't have koalas in Britain, because baby koalas cannot swim very far. Much as though they'd like to be in Britain. Okay? So, faunal reconstruction means using the distribution of groups of benthic fauna in order to determine where there were relatively wide oceanic separations. And this model is based on such faunal reconstruction. In the Arenig, which, as you know, is in the Ordovician, which part of the Ordovician?
Lower.
Early Ordovician, okay. Arenig is in the early Ordovician. There was a wide ocean between Scotland, you see that little bit there? That's a little bit of Scotland, just above the point of my arrow. And the little green ellipse is where the southern uplands is going to be. It wasn't at this point in the Arenig. And England, which you might just about be able to discern down here. And as the Ordovician progressed into the Caradoc, the middle part of middle upper Ordovician, the ocean contracted specifically because Avalonia, this little microcontinent on which we are proud to reside here, split away from Gondwana to the south, and happily drifted northwards, because it didn't have a larval stage and it can drift across the ocean. Okay? So in the Caradoc, which is when the northern belt of the southern uplands was developed, we have Avalonia peacefully drifting northwards, still with a large, or relatively large, Iapetus Ocean separating Avalonia from Laurentia. In the Llandovery, the early Silurian, when the central belt of the southern uplands was developed, the ocean between Avalonia and Laurentia is still open, but narrowing substantially, despite collision between the microcontinent of Avalonia and this object here, which if you look closely you can see Scandinavia in. This bit is called Baltica, as illustrated up there. So Baltica collided with Avalonia at some point in the early Silurian. And finally, closure took place between Avalonia and Laurentia. Avalonia got stuck onto Laurentia in the Devonian. So that's the view based on faunal provinces. This is an alternative view based on structural considerations. On the top left here, 440 million years ago, roughly the end of the Ordovician, the structural considerations show the Iapetus Ocean already very narrow at that point. Here's Scotland, there's England on Avalonia, and the ocean has completely closed by 420 million years ago as a result of the Scandian orogeny, which was mentioned by Anna hopefully. The Scandian orogeny is the result of closure between Baltica and Laurentia, and is thought to take place around 425 or so. So it had been completely closed in this view by the end of the Wenlock, implying that closure of the ocean actually takes place during the formation of the southern uplands. And the thing to note about this model is that collision between Avalonia and Baltica is later than it was on the faunal model. So we can contrast these two models. The faunal model suggests collision between Avalonia and Baltica in the late Ordovician, perhaps, and then collision with Laurentia in the Devonian, 410. The structural model suggests Avalonia-Laurentia collision at about 425, and then final collision with Baltica about 410. How do we tell which model is right? By understanding the stratigraphy and structure of the southern uplands, which is effectively what you've been trying to do in the practical. And you had this map in the practical. Incidentally, I've added a green star, that is Dobbs Lynn, where we visited. So Dobbs Lynn is in tract 6 of your section, and if you look on your list of, in your practical handout, it will, I think, says DB for tract 6, does it not? Or did it even say Dobbs Lynn? It says Dobbs Lynn. And it has DB as a dot on the map. Okay, so that's where you went. We now interpret the belts of shale that you saw crossing the Sankar map as faults with shales next to the faults, not as little isoclinal anticlines, as was suggested in the cross-section of the Sankar map. We know that that cross-section is wrong because that cross-section predicts large amounts of basalt at shallow depth, and large amounts of basalt would have a strong gravity and magnetic signature which is not present under the southern uplands. So there's no evidence for significant amounts of basalt at depth under the southern uplands. Peach and Horn were the gentlemen who did the original mapping of the southern uplands and produced the Sankar sheet. They recorded the outcrops correctly, but their interpretation of the outcrops was incorrect and has now been changed. Remember the point that these geological maps, indeed all geological maps, including the ones that you come to draw next summer, those of you who are doing geological mapping, all geological maps are interpretations, and your understanding of geology as the mapper inevitably colours your interpretation of what you see. Why has the interpretation changed? Because in the 1970s a gas pipeline was put through the southern uplands, essentially paralleling the M74 motorway that we drove along, and which goes up through this sort of area here. And this exposed a previously unseen cross-section all the way through the southern uplands. The southern uplands are not fantastically exposed. There is not that much outcrop within the southern uplands. And it needed this gas pipeline with continuous exposure to produce a very different interpretation than the original one by Peach and Horn. So, there's a nice photograph of Peach and Horn for you. Peach and Horn were eminent Victorian geologists, and it was they who were first responsible for understanding the structures associated with the Moyne Thrust Zone in northwest Scotland. In particular, they established the structures of the Moyne Thrust, how it was put together, in the region around Erebol, which is one of the mapping areas for next summer. And Peach and Horn, while they spent their summers up in northwest Scotland, they occasionally found it a little bit difficult to cope with the winter up there, and they had some light relief in the southern uplands, southern uplands in the winter, which they did on horseback with lackeys floating around on foot, running along on foot beside their horses, bringing them lumps of rock to describe. So if you want to organise your mapping well, that's a good way of doing it. The revised interpretation is largely a function of this gentleman, Stuart McKerrow, and his research students. His research students include Jeremy Leggett, who published the first interpretations of the southern uplands along the lines that we'll go into. Jeremy Leggett is now, or has been until recently, chairman of Greenpeace. And other research students of Stuart McKerrow's who worked in the southern uplands were Chris Elders, and he was also my tutor at university, so I know him quite well, except he's dead now, unfortunately. So the work by McKerrow and his students led to something very similar to what you have been putting together during the practical. This is a little bit more detailed than what you did in the practical, but it's basically the same sort of thing. Okay? It shows a series of fault-bounded tracts It's more detailed because we have 2A and 2B, 3B, and for some reason 3D. I don't know why we go 3C and 3A, but never mind. And these tracts are put together versus the graptolite zonation of the southern uplands, which we assume to be proportional to time. And the most obvious thing that you can get from that is that the turbidite sequences, the sandstone sequences, are always at the top, above black shales, and the turbidites get progressively younger as you go southwards in the southern uplands. So in the northern belt, the turbidites are Caradic or Ashgill. In the central belt, the turbidites are Llandovri. In the southern belt, the turbidites are Wenlock. Sadly, as you will have noted on the map, there are some of these sequences that don't have graptolites in them. For example, this sequence here. And these are placed on this section in a way that they fit the model. And clearly there's an element of doubt in what we do with sequences that are unfossiliferous. So how would we interpret this? A very simple way of visualizing this sequence is that we have an ocean to the south in which pelagic shales, the Moffat shale group, it's those black shales that we saw with the graptolites at Dobbs Lynn, in which the Moffat shale group are deposited, and a turbidite fan derived from the north has gradually covered the ocean floor to the south. So as time progressed, more and more turbidite has been derived from the north, and it gradually moves further out into what was previously an oceanic environment. So that's a possible model for what we can see in this change in time of the onset of turbidite sedimentation. It has problems, particularly this turbidite fan has to be extremely long-lived. It's got to last through the bulk of the Silurian and the upper Ordovician, something like 30 million years or so. It also doesn't explain the fact that the turbidites show paleocurrents that run from northeast to southwest. If this was a prograding fan, the paleocurrents should all be derived from the northwest and moving to the southeast. Okay? Axial. The turbidites are characterized by having axial paleocurrents. The older interpretations, such as seen in these Sankar maps, is a static interpretation where you had a relatively elevated region of the ocean floor called the Moffat High. Remember, we drove through Moffat. And on the Moffat High, black shales were supposed to be deposited, with troughs surrounding this high area on the seafloor, and the troughs accumulated the turbidites. This sort of model would mean that the turbidites should be of the same age, both to the south and the north of the black shale sequences, so it doesn't account for the age relationships seen on this sort of sequence. Other models are dynamic in character. They're things that develop over time, and in these we need to consider the relationships between the stratigraphic sequences and the faults that were observed along the gas pipeline cross-section. And the most important observation that is made when you look at the individual thrust tracts is that within each tract, separated by thrusts, the sediments young towards the northwest. We saw this at Dobbs Lynn, where we could demonstrate Ashgill graptolites, followed by Llandafri graptolites, followed by turbidites, as we walked in a northwesterly direction towards the waterfall. Overall, however, as you've seen on the geological maps, the stratigraphic sequences young towards the southeast. The accretionary prism model was developed by Leggett and McKerrow and explains these observations very well. In this, the black shales are deposited on oceanic crust, for example, at A here. So here's black shale being deposited on oceanic crust. And the oceanic crust consists of basaltic material, itself overlain by radiolarian cherts, the sequence that you saw in the Sankar map, basalt overlaid by radiolarian cherts, overlaid by black shale. As ocean crust enters the subduction zone, around point B on these cross sections, you get rapid deposition of turbidites on top of the black shales. And then, subsequently, slivers of ocean crust with the overlying shales and turbidites get scraped off, as at point C in this diagram. So each of these slivers represents a, separated by faults, represents a segment through, or section through the oceanic crustal sequence of basalt through to chert, through to black shale, through to turbidite, which is then accreted onto the Laurentian continental margin. Looking at the Sankar map, you will have seen that you only see basalts, i.e. true oceanic crust, right in the northernmost part of the northern belt. And a possible reason for that is that it's actually very difficult to develop thrusts through the basaltic sequence. It's much easier to develop thrusts at the base of the ductile black shale sequence. So, more commonly, the base of the sequence in each tract is black shale. With time, you remove older tracts to the north as younger tracts, younger sequences enter the trench. So here is this is tract 1, having been accreted to the Midland Valley. There's tract 2 accreted, and tract 3 is just developing in the Craddock here, and is about to be accreted. In the Llandafri, we have tracts 1 to 4 already accreted, and we're about to accrete tract 5. So the older sequences that you find in the older tracts, the more northerly tracts, get rotated to the north as a consequence of the dip of the subduction zone, so that within each of these tracts, within each of these sequences, you get the oldest material closest to the thrust fault and the youngest material at the top. So that's why we get the northwest younging. If you look, there are little arrows on this bottom line here. So this arrow, these little arrows here, show the younging direction within each of the tracts, getting progressively younger towards the northwest. In contrast, the overall sequence youngs towards the southeast because younger tracts are accreted further towards the southeast. Note that it is the onset of turbidite sedimentation that gets younger to the south. That's what you showed in the practical on your graph paper and was clearly visible in that section from Makero's paper. The bottom of the shale sequence can be very old. In your graphs, you sometimes see the base of the shale sequence going quite low down into the Ordovician. And that's because the shale sequence can be deposited over very long periods of time on the ocean crust. The turbidites ultimately have to be derived from the northwest in lodes or fans, and then the currents within the trench flow towards the southwest. There's a very good analogue for this in the present day in offshore of Burma, where turbidites derived from the rivers flowing southwards from the Himalayas are transferred laterally about 1,000 kilometers southeastwards along the Burmese coast by axial paleocurrents. But some possible problems. The youngest shales that we observe are Plandovery in age, indeed mid-Plandovery in age. There are no shales within the southern belt. Southern belt is just turbidites. So, if we haven't got black shales in the Wenlock, perhaps the ocean has closed by then, which is what was suggested on the tectonic model. But the same structural style of separating these tracts of rock by faults and the presence of deep water turbidites continues throughout from the Plandovery into the Wenlock. So that doesn't really suggest that closure happened in the Lake Plandovery, not if the deep water sedimentation continues. It's just that there isn't much ocean left, and most of it is being covered by turbidite. Ultimately, northwestward derived turbidites get into the Lake District sequence, as we'll be discussing next week. But they don't get there until the Ludlow. So that suggests that the ocean still remained through into the Ludlow. There's a problem. The northern belt, the Ordovician, part of the southern uplands, contains pyroxene-rich sediments in places within the turbidites, and the pyroxene-rich sediments are southeasterly derived, unlike the more common axially or northwest-derived ones. And these imply an active volcanic source towards the southeast. This would not be possible if there was open ocean towards the southeast. So, Stone and his colleagues, Stone is a really good name for a geologist, of course, proposed instead that the southern uplands developed in a back arc basin environment with a volcanic arc to the south. So this is his model for it. This is the northern belt developing as turbidite fans from the northwest axially, and the odd turbidite fan coming off a volcanic arc lying towards the southeast. Okay. Red heading should be up first. Some problems with that model. where is the arc? Now, we know that there is Ordovician arc within the Midland Valley, at least we do if we answer the question properly in the test. And it seems a bit strange having an arc lying off to the south of the southern uplands in the Ordovician as well. Arcs are not very easy to get rid of. They're relatively buoyant, they're made of massive igneous rock, and it's not that straightforward to dispose of them. So, the interesting question is, where is the arc? Perhaps you could derive the volcanic detritus, these pyroxenes, from an ocean island within open ocean to the south. That's a possible scenario. It's worth thinking that what sort of volcanic rocks do you find pyroxenes in as phenocrysts? Mid-ocean ridge basalts? Not really. Very occasionally, but not much. So certainly wouldn't be mid-ocean ridge derived. Ocean island lavas and arc lavas contain pyroxene phenocrysts quite commonly. So possibly they're derived from an ocean island. And within the northern belt of the southern uplands, there are isolated occurrences of basalt that do have the chemistry that are typical of ocean island basalts, such as Hawaii, for example, which you know in detail about half days later this week, do you know? Yesterday, indeed. Right, what timely. And these basalts with ocean island basalt chemistry tend to form little bodies which might represent accreted ocean islands on the margin, on the Laurentian margin. I should have said that the basalts that you find in the base of the sequences sometimes have mid-ocean ridge basalt chemistry. Not all the time, but sometimes do. So what do you think about these two hypotheses? The evidence, we said, good. Evidence in favour of an accretionary prism model is that the chemistry of some of the basalts, not all of the basalts, underlying the cherts and pelagic shales, resemble mid-ocean ridge basalts. We have a very long-lived pelagic environment. Black shale deposition at Dobbs Lynn, Moffat area, lasted for at least 25 million years. Very long-lived environment of black shale deposition. The sedimentary style, where we get trench sediments, the turbidites, deposited on top of our pelagic black shales, is in favour of the accretionary origin, and this structural style, the stacking by thrust, strongly suggests it. And this leads to the notion that closure of the ocean was post-Silurian, or at least late Silurian, because we get this stratigraphic style, the black shales overlain by turbidites, we get these structural sequences all the way up into the Wenlock, the middle Silurian. In favour of a back arc origin, the presence of this volcanic detritus, but you could possibly, which we've said you could possibly explain as intra-oceanic ocean islands, though the chemistry of the pyroxenes is a bit closer to arc pyroxenes than ocean island ones. The missing arc is a problem. And in general, the groups of people who favour a back arc origin favour a Silurian closure for the ocean, and they would argue this because there are no basalts present in the central and southern belts, so there's no evidence of ocean floor, real ocean floor, oceanic crust, in the central and southern belts. But still, we have these thick shale sequences, and you still need to explain why the structures are continuous over such a long period of time. There is now new evidence from detrital zircons in the sediments that contain, in the turbidites that contain this volcanic detritus. The zircons associated with the volcanic detritus, with the pyroxenes, are Precambrian in age, 613 million years. There we go. And this suggests that the detritus, the volcanic detritus, assuming that the zircons are derived from the same place, is much older than the host sandstone, which is Ordovician, and therefore the volcanic material is not evidence for a contemporaneous arc. Instead, it's probably derived from the remote south, maybe as far as Abylonia. And that was published by Phillips et al. In 2003, and since that paper has been published, Stone has written another paper in which he accepts that he was wrong, and he believes I think from that basis he now accepts it's probably an accretionary crystal. But it's a nice set of papers to read. They're all on Moodle. And that's it for the afternoon.